race car project costs and how to use simulation programs and manufacturing techniques and innovations to help with that. That's what we're going to be going through in this episode 2 of our er8 the tech series. And on episode 1 we went through the basics on how to get into the correct mindset of figuring out what things are important and what things are not important, and what kind of information to take in, and how to be able to filter that. And now we're going to, in this episode, going to be looking at how to actually confirm and verify that the things you are looking at are actually meaningful and are going to help provide gains for your project. Because the end result is, of course, that you're always fixed on your costs. So the faster a car and the more efficient you can have your manufacturing stuff, the more performance you're going to get out of your car with the same amount of resources. And this is, of course, one of the main aspects for any project. But once you know the theory behind it, okay, so we want to increase our cornering speed by as much as possible within regulations that allow for that. But then how important are different aspects of these, and how is tire flex going to influence the feel of the car, and how are different differential lock situations going to affect this, and how is all of this going to work together, and how are we going to figure out that once we design a car that we don't notice in testing that, okay, we have some big vibration problem that we need to solve, and this is going to create some big redesign need for this, or that we're going to need to drive the car in a different way, that we're going to lose 4 or 5 seconds whatever per lap. So these are important things to sort of figure out beforehand without testing as much as possible. Of course, you're never going to be absolutely accurate, but there are some big advantages that can be had with testing with simulation or computer testing in relation to real-world testing. And the main aspect of that, of course, is the data that you can gain from that is so much more detailed, and you can very, very cheaply get all the data you want, basically, which is very difficult to do with real-world testing. But of course, correlation with the real world is something that needs to be tried afterwards. Let's go through some of the basic software we use here at the moment. So for designing, of course, you need a CAD program to design the actual components for the car. I mean, if you want to do things cheaply and efficiently nowadays, there's no other way than draw everything on the computer, and then you can also use that information to run the simulation stuff to see how well that is actually going to work on in the or close to a real world scenario. And then you can also, of course, try different components. How is the differential lock you can afford to buy for your project, or what kind of components are going to be more important, and so forth. We use SolidWorks here at Elmer Racing. That is a commercial CAD program that is not super cheap, or depending on what components you use for that. The very basic CAD package for that is actually not very expensive, so that is probably within the reach maybe for average, or at least the sort of higher end racing teams, definitely. But then doing advanced FEM runs on the components and potentially composite strength calculations, then the packages start getting really expensive, and if you need to have multiple users, then those start getting expensive. And there are potentially some open source solutions available for let me see if I have this in some tab here. So there is a FreeCAD available. I have actually not tested this yet, so I was kind of bringing up some suggestions and ideas here also. But if you do have knowledge about how good this FreeCAD works, and how it compares to commercial CAD programs that are available, then feel free to leave comments on this and other suggestions possibly also. So I know there are CAD programs available that you run from a server remotely with internet browser interface, and yeah, that's probably not what you want to do, because yeah, then your information is hosted on some server and you're not controlling that yourself, so that can potentially create lots of problems. But if FreeCAD is something you know something about, or have other suggestions for open source CAD programs, then help out the other viewers and leave comments on this and other suggestions or links to videos that go through these topics. But yeah, once we have the stuff done in CAD, we want to run simulations on the actual vehicle, and there are some ways to do this. One very popular method that I know is running very simplified models on some simplified track and run sort of what are they called, weight analysis or something like this. So you run basically multiple simulations of that with varying different parameters to see which parameters will influence the lap time the most. But yeah, that's not really something I like doing a lot, because if you understand the basics about what makes a car fast, and you will know that if you checked our episode 1. So once you know that, you really want to check how the whole car is going to perform together completely, basically. And to do that, I would definitely suggest running a full vehicle dynamic simulation with the driver in the loop also. So that basically means running a computer simulation race game or something like that. There are different ones available, but as far as I know, er8 is by far the best one available for that. Yeah, so this is the er8 homepage. The software is available on Steam for not much money at all. It's sort of not a freemium model, but yeah, their business model is quite good. So it's very, very cheap to buy the base package, and then you can add on different mods that different people make for that, and they of course make very high quality mods. The makers of er8 also themselves that you can purchase, sort of, well, not upgrades, but more cars, more tracks. Different people can add stuff in that, and that is something that I would highly recommend, because you're going to be doing so many compromises, optimizing your cost, basically. That is the most difficult optimization process for a race car project. And yeah, you can check, okay, we need whatever differential that is available cheaply, or gearbox or something, and there can be easily 40,000 euro price differences between these kind of components. And if you can run a more off-the-shelf component that you can make the car work with, then yeah, that's 35,000 euros potentially that you can save for doing more advanced aerodynamic package on the car that is going to potentially influence the car performance much more, if you can get the car to work with that. And the only way to really figure that out is to run a full vehicle dynamic simulation. So you're not going to be able to do that with a simplified sort of these weight analysis type stuff. Basically, yeah, it's better if you can do the weight analysis stuff mentally in your head and figure out, okay, what are important things and what are not, and how much sort of things can we play around with roll bars and differential locks and camber angles on the car. But yeah, we're not going to get into details on that now, but the sort of basics on the simulation and manufacturing stuff. I do believe I have, so this is the setup we're running. It's very important to have a high quality force feedback wheel. There are even better ones that I would prefer to get, but they again require more time to set up, and yeah, time is money, especially when we're doing this really as a side project. I mean, we're not a professional car manufacturing or designing company at all, so So we need to keep the amount of time used for making this project as low as possible. I mean, yeah, we actually design and manufacture racing engines and components. So yeah, we're put time into making the Thor engine and billet collectors and these types of stuff that you know us from, and need to keep the time expenditure for these types of er8 projects and different components related to that as low as possible. So yeah, this was relatively quick to get and easy to install, and is sort of high enough quality. So this is not a direct drive wheel, but a reasonably high force feedback wheel, which is very important with high downforce cars, because the force feedback level is going to be much higher, or depending on the suspension geometry you have designed. But if it's designed in a way that I would think is good, then you're going to have much higher force feedback at high speed corners than at low speed corners, but you still want to have the sort of feel resolution in the steering wheel at low speed corners. So you need to have a wheel that will get up to almost realistic levels of steering wheel forces. And this is the datalog screen. So there are plugins available for r8 to get datalog out to Motec standard format, and then you can run the Motec plugin to do this, and you can run all kinds of manipulations to get the data in whatever format you want to do. So we have a model of, it's not a laser scanned or super accurate model, but a reasonably accurate model of the Sydney Motorsport Park, the circuit layout that World Time Attack is run at, that this car is basically being designed for mostly. And I think something like this is, I mean, of course we have lots of different layout versions for this, but we have force vectors basically, or lateral force and longitudinal force on all different wheels. We can drag this through the whole lap and see, okay, we have some problems that the car is pushing in some corner, and okay, so we can check out what are our wheel loads and how much force in which directions are the wheels applying that or using the tire friction in relation to the lateral or what is it, lateral, so the vertical force applied and how that's being used in which direction at which tires. You of course want to reduce the amount of force that the tires are fighting each other with, because that is, all of that force is being lost from actually increasing your cornering grip and speed. But yeah, these are things that would be extremely difficult to do, or well, not maybe extremely difficult, but expensive and time consuming to test on a real car in the real world, but it's very easy to get this data out of running computer simulations. So this is one of the reasons why I really like doing computer simulations and try to do that as far as possible. But again, as we went through in episode 1, it's important to know what kind of simplifications you're doing and what how big of an error you're making with these simplifications, and in which direction that error is, and is this potentially something that is going to affect the direction of how other aspects of the car will influence or not. So hopefully not. So if you like add front downforce, then is the car going to behave in the same direction as the real car will or not? So these are relatively important things. What else were we going to be going through? And the simulation importance. So when you Le Mans Group C cars or the Pinnacle F1, the turbo cars in the I believe that was the early 80s or something, when they had the absolutely crazy cars and rules of course the cars are probably faster now because the aerodynamics have advanced so far, and the tire technology also. But then you had all kinds of different cars running, and there was a huge expenditure to do testing on cars, because you needed to manufacture a model, run that in a wind tunnel, and when you then you got some results for that, and you needed to do a new design iteration, and it was really difficult to get detailed data. Of course you can get very high quality data on the whole model and how that performs, but how the different areas in the model perform is very difficult to do, and that's kind of the same thing with the whole vehicle dynamic simulation. That when you run that on a computer, you can get the data from each and every point of the car. So when you do an aerodynamic run, and I could actually bring up the software for that. So we use OpenFOAM to do the CFD stuff, and that's open source project that they the company that develops that also offer professional services for that for other companies. Basically a basic open source company model. With this you can some examples running there. That is actually very small. Let's see if I can get this bigger. So you can see some form of stuff, how you can visualize this. So you can see how the flow behaves at each corner and what the pressures are over large areas and how that influences everything, and that will help you develop stuff so much faster than doing physical models. Of course, you always need to double check the models, especially CFD stuff. It's just a weather report as long as you haven't correlated that with the real world, because even if you know what you're doing, it's still very, very easy to get a result that has nothing to do with reality at all. So there's no such thing as, okay, the model is off by 5% or something. In CFD, it doesn't work like that. With the FEM stuff, so strength calculations, you can be reasonably sure that when you're doing a model and you basically know what you're doing, so that you're not doing mistakes and you're taking the corner mesh size into account accurately and stuff like this, that you know, like, kind of how accurate you are. With CFD, no, it doesn't work like that at all, because there can be a tiny difference in some area can totally change the whole solution for the flow field, and the whole result will be completely different. Of course, you still get some force values out of that, but they have like no correlation at all with real world stuff anymore. So if you change the angle on some wing or something, but the flow field is completely different in the simulation from what it is in the real world, then the end result will be completely different. Like you might end up increasing rear downforce when in reality you would decrease rear downforce or something like this, and then the simulations are not very useful anymore. Once you sort of have done some testing and know that you're hopefully not doing any big mistakes and the thing is working more or less accurately, then you can do design iterations and improve the design way more efficiently. So you can have a one-man CFD team can basically make a design with better than the Le Mans Group C cars, for instance, even with the factory support, running wind tunnels for I'm not sure how long they ran that, but I would assume probably many months or something like that for the car designs at huge expenditures. And now with computer technology, you can do that at a much reduced cost. So it's possible to do these super fast RP968 cars and hopefully er8 car also with way smaller expenses. So that is one of the main things nowadays that is very good. Then manufacturing stuff. Unfortunately, I don't have any good slides for that, so maybe I'll just leave this on here. So manufacturing techniques is also something that is very important for the project cost as a whole, because you can very easily end up with, we need to start 3D printing large parts or something like that, and that gets very expensive. As long as, if you need to 3D print large metal pieces, then it gets very expensive. Of course, you can 3D print large plastic pieces quite cheaply. And then do you need a milled mold, for instance, to do some carbon fiber overlay, or do you have potentially cheaper ways to do that? And that is something that we have innovated a lot with here at Elmer Racing, to get the manufacturing done as cheaply as possible. For instance, you can clearly see that on our Thor engine. I mean, the price performance ratio on that engine is insanely good, which is only a possibility because we do the design and manufacturing in-house, so we can take the the manufacturing process that we want to do into consideration when we design the engine and size the components and all of this stuff. So that helps immensely with the cost of that. So the Thor engine, for instance, has a power to weight ratio better than even the V10 pretty much unregulated F1 engines, but it costs like under a tenth of a single engine or something like that. So it's, I mean, the gains that you can have are just insanely high now. And same goes, of course, also for the car bodywork manufacturing, suspension components manufacturing, or those are actually very, very simple to do if you design the components sort of correctly. But yeah, those are important things to look at and sort of think about when you're designing your car, and how the layout is and what are important things for which aspects. And if you make some mistake or we don't have time to do the simulation stuff and end up running the car, and then you might figure out that the 40,000 euro gearbox that we have on the car isn't optimal, and we could have run with a 10,000 euro gearbox instead. That would have been even better, or something like this. Then that ends up getting really expensive. Or you're not really sure of the suspension geometry, or what's that going to be when you're designing the chassis or something like that, and you end up putting forces through the chassis through areas that aren't designed for that, and you end up needing to add stiffeners or something. You can end up with a car very easily that is 20 kilos heavier. That's even with a good design. If you have a car that is just, the chassis is just designed, how should I say, poorly, or in sort of conventional means or something like that, you can easily end up with a chassis that weighs 50 kilos more or something like that. And yeah, as we went through in episode 1, if the downforce levels are high, then the weight of the car starts getting very important also. And if you have a car that is 20 or 50 kilos heavier than what it needs to be, then that is going to be a huge detriment to your performance. So it is important to look at all these kinds of things, and this is something that I don't think there is any really good scientific solution to. So this is sort of more of feel and what you really think about things. So yeah, try to differentiate what is scientifically proven and what is sort of stuff that you need to have a sort of feeling for, and try to base that on science as much as possible. But yeah, that was the short version, and hopefully we'll see how this goes. And if you want to continue with the series, we're probably going to do one more episode at least before we check on what the sort of overall feedback is and how much we want to improve. Of course, we checked feedback already to try to improve this episode too, but to see if we continue with the series or not, and how much views we have, and how much you liked it. But we did get a lot of feedback from episode 1, so it looks good so far. But yeah, I'm Oscar from Elmer Racing, and this has been episode 2 of our er8 The Tech series. See you in episode 3, hopefully. Bye.